Einstein's theory essentially predicts its own downfall. It says that, say, at the center of a black hole, let's say in a collapsing star, that there's no cutoff. It drives you in that sort of gravitational collapse to a point of infinite density, infinite space-time curvature. So it's a so-called singularity. But there are very good reasons to believe that that's not right. One of them is that we strongly expect black holes to be temporary structures. So they return their energy to the universe again, almost certainly, and this is through the process known as Hawking radiation, which is a first step, one of Stephen Hawking's great contributions. It's a first step towards bringing quantum mechanics and gravity together. And it has with an audience like this, it has the benefit of being quite easy to explain what's happening, actually. So I can do it if you want, which is that, so Hawking realized that quantum mechanics tells you that the empty space is never empty. So in particular, you can picture particles and antiparticles pop in and out of existence all the time. And so they pop into existence, they can borrow energy from the vacuum, if you like, for a certain amount of time before they return it to the vacuum again. And actually, the more energy they borrow, the less time they're allowed to borrow it for. That's called the energy-time uncertainty principle. So it's a fundamental part of quantum theory. So when you imagine on the so-called event horizon of a black hole, you get these particles pop in and out of existence. Just let me say, by the way, that these effects are measurable, and it's one of Feynman's contributions, one of the things he got his Nobel Prize for, showing how that in the light from hydrogen atoms, those little fluctuations have an effect, and you can take them into account. So we know they're there. So imagine on the event horizon of a black hole that the particles pop into existence, and they're going to come back together again. But one of them they end up on opposite sides of the event horizon. That means that they're what we call causally disconnected from each other. They can't come back. You've got one that's inside the black hole, if you like, can't get out. So what happens? Well, the particle that's outside is made real. It essentially radiates away, and it gets its energy from the black hole, ultimately. So the black hole radiates, it has a temperature, it shrinks because it's radiating energy away, and ultimately it returns its energy back to the universe again. So you sort of know that there's no end of time there. There's nothing really wrong in the center of a black hole. It's just that the theory doesn't work, and it must be that quantum effects and these things, that something must stop you having these infinities and infinitely curved space, and that's the challenge. So we know there's a better theory. The theory predicts its own downfall. Same at the Big Bang, by the way. But we don't know what the theory is. We've not been clever enough to put it together. But the first steps are being made with things like Hawking radiation. Particle physics is a game of statistics, essentially.